Okay, we finished the stabilization limits for the premise friend and the diffusion friend, and even for the intermediate regions between these two categories. And now we shift a little bit to discuss the critical ports Reynolds number for various frames in air. And this table gives you an idea. Actually, though, this is a so-called critical Reynolds number corresponding to the transitions to frame transitions from the laminar to the turbulent, okay, in this region, the critical injection velocity, and you can, based on the pore diameter and the viscosity and also density of your fuel jets, then you can identify the critical Reynolds number for the transition of diffusion or these transition regions. And this table tells you for the hydrogen, actually, they have a smaller critical Reynolds number, and the city gas, actually, you can look at here. For the hydrogen, actually, they are pretty much light molecule, where they're small, and then they will induce the turbulent flow earlier than the critical Reynolds number is small. Okay, and the interesting thing is if you increase the here, they can say this is hydrogen, and the critical Reynolds number for the transitions is around 2000, right? But when you have some premixing, there is they show you with some primary air. Primary air means that you initiate a premix certain amount of air into your fuel jet. Okay, they have a certain amount of premixings. Then the Reynolds number will reduce to the or increase to the 5,500 up in the range of 500, 5,500 and 8,500 in this range. Okay, similar way for the city gas, when you have a primary air, the Reynolds number increased. What is the meaning of Reynolds number, critical Reynolds number increase? When you have a larger critical Reynolds number for the transition region, means the turbulence influence initiates laterally, can be postponed to the higher velocity, which means it is not easier to produce the turbulent jet diffusion frame. Okay, it's more stabilized compared to let your frame feature to go back to the laminar situation. And this is a very easier to understand when you have some premixings. Okay, now you will have a more the bending will more like a premix type in the lower portion of your jet diffusion frame, and those heat release will produce the high temperature zone. Temperature high, when you have a temperature high, actually they give you the influence on the viscosity for your gas flow. If you have a high temperature, then your viscosity will be reduced. Okay, this is just opposite for the liquid. For the liquid, if you try to heat the liquid, the liquid viscosity will be reduced. But for the gas, when you increase the temperature, the viscosity is increased too. I'm sorry, I made a mistake in the previous sentence. Actually, for the gas, when temperature increased, the viscosities will be increased too. Okay, but for liquid, when you increase temperature, the viscosity reduced. Therefore, usually for the piping, for the viscous fluid, you try to transport it as small as possible to make it easier to flow. Usually, you try to heat it up. When you heat it up, the viscosity is reduced, then flow will move smoothly. Okay, this is for liquid, but for gas, it's a complete reverse. When you increase temperature, viscosity increase. When you have a higher viscosity, that means your Reynolds number will be reduced, right? Your Reynolds number will be reduced. Okay, then for example, here you can see, as I explained earlier, for the same flow conditions, this is a cold jet for the figure A. This is a cold jet structures. They have a very strong turbulent interaction for between the ADs. But when you have a frame exist here, that means that the flow structure become more smoothly, more like the frame laminar shape, and they do not have very strong turbulent AT interactions. And this tell you when you have a frame exist, then the flow experience the heat release through the frame temperature increase, then viscosity increase, and by this the increased viscosity will lower down the Reynolds number corresponding to this jet. Okay, for the cold flow, in this instance, the Reynolds number is pretty much high, but when you ignite it, the temperature increase and viscosity increase too, then we'll reduce the Reynolds number to a small one and lower than criterion for turbulent flow. Then this flame will become more stable and a bit more without those kinds of turbulent AD interactions. Okay. But for the same thing, if you have a chance the flame dip off in this region, okay, in the lower part regions, the turbulent AT still have a strong interaction because this is a cold flow, relative small temperature. Viscosity increase is not too much, Reynolds number, then they will become still remain the large value higher than the criterion for the turbulent intensity, then the flow will return to the turbulent flow structures. Okay. Now the final part I want to mention, especially for the diffusion flame, more focus on the so-called the soot formations. Okay. Usually for premise flame and the diffusion flame, most of them we can see the yellow color flame. But for the premise flame, usually you can have a yellow flame, especially for the few rich premise flame, especially for the higher hydrocarbon flame. For example, it is very difficult to see the methane flame as a yellow color because they only have one carbon atom exists for a methane molecule, right? But for the propane, for the butane, they have more carbon atoms in a given few particles. Then they can produce a more sooty flame. The carbon particle becomes stronger. This is the why people will think about the carbon emission, right? Because when you burn the different kinds of fuels, which fuel will produce the larger amount of carbon dioxide in your downstream side. Definitely, people understand when you burn the coal, because 1 kilogram of coal contains more carbon compared with the one kilo more of methane. They have a much higher carbon content in coal. Then people were against burning the coal because they produce a lot of carbon dioxide emission. But people allows burning the natural gas because the methane contains less carbon in the molecular structures. Okay, this I just explained why we use the natural gas instead of burning coal in recent years. But actually, when you burn in the methane, still produce a carbon dioxide. The better one is you just burn the hydrogen, then you do not have a carbon dioxide. But when you think about when you burn in the hydrogen, you will produce the water as the major product, right? But actually, the water H2O actually is one of the so-called the greenhouse emission species, right? And they even have a stronger influence compared with the the carbon hydrogen fuels, carbon fuel, because based on the same amount of the mass. Okay, actually water has a strong greenhouse effect compared with the carbon dioxide. Yeah, you can have a different kind of thinking to look at the problem you may have. But we go back to our discussion on soot formations. Here, I try to mention, definitely we already explained there is a lot of soot formation inside of the diffusion flame because there are fuel and the separation between the fuel and the oxygen and the influence coming from the natural convections. And for a rich premise flame, you will have a strong possibility to have a soot particle occurs in a rich side of the premise flame, but uh, depends on what kinds of hydrocarbon fuel you used. You have a higher concentration of carbon, then you will have a higher soot particles occurs in the premise frame. Okay. And usually when we mention the soot formation, actually those soot formation accompanied with the storm radiation. Those yellow color radiations, it will increase the heat of the transfer. That means the radiation heat transfer. This is another important thing is soot formation is not a good one because they will produce pollution, right? They have some particular pollutions, but in the inside of the combustion zones, actually they will enhance the thermal radiation. Those thermal radiation is the major heat transfer in the combustor in the combustion zones to enhance the heat transfer. Now you need to think about can we have those kinds of intense heat radiations in the combustion zone, and later on try to eliminate those kinds of soot. Then people will think about the so-called stage combustion. Initially, they have a rich burning. A lot of carbon will exist in the high temperature zone to enhance the radiation transfer. Then later on, we try to supply the so-called secondary air to finish all the burning out. Then you will not have a soot or particulates occurs in the downstream side. This is the way people think about how to control the combustion process. You still can have a strong radiation heat transfer, but minimal emissions coming from the soot particle. Okay, but anyway, here I want to give you some experiment, especially to mention, to let you know, since when you have some carbon atom released from the thermal pyrolysis, now if they do not have they do not stay for a long time in the flow structure, in the flow regions, they will move to the other region. But in many cases, they have a longer residence times to finish the oxidation. Now the molecules carbon molecules will hit together to produce the so-called carbon particle. Actually, the residence times of your carbon atom is an important considerations, important criteria for the soot formation. Now I try to bring those kinds of rotation motion to give you the idea to think about the soot formation. It not just governed by the concentration of your fuel and also the concentration of oxygen and also the residence time of your flow. Now we try to introduce the flow vorticity into the diffusion frame in the opposed jet flow. I hope you remember this structure. You remember we have a so-called counterflow, opposed jet flow, and we make it rotate, right? When you rotate your burners, then the circulation force near the burners will push your axial momentum to radial, right? And you may not, because those axial momentum will transfer to the radial momentum, the axial momentum will be reduced. When the axial momentum of your flow reduced, that means that near the stagnation point, the flow velocity, flow outward will be reduced. Okay, let's look at when you have a stagnation plane like this here, and the flow moving like this, right? Like this way. When you have rotations, those radial velocity along the stagnation plane originally they may have this large velocity, but with the increasing of flow vorticities, omega, the rotation speed, then the velocity will be reduced to the minima. Then the flow will move to a different direction. Actually, that means the flow, because they will diminish to the zero, right? And the flow will reverse from the outer surrounding to the inner region, and which means in this case you will produce a so-called recirculation zone here. Okay, this plus tell you when you increase your flow rotations, then your outer flow will be sucked around the stagnation surface into your flow, and here they will produce the so-called recirculation regions. And this is ideal structures because we assume they are symmetric, and you will have a pair. Okay, for our diffusion frame in both in upper and the lower flow, and those the region will be increased. Okay, And here we'll find out the widthness of the recirculation increase, and to a certain value, because the loss flow coming from the outer region, they will bring some fluctuation into your flow region, and especially in the center region of your flow near the stagnation plane, the flow velocity is relatively small, and the major velocity is small, easier to be influenced by the outer perturbations. Then they will create those kinds of AD structures. Let me go back to our slides to give some explanation to you. Okay, this is just the previous slide to tell you the system we have. There is the upper burner and the lower burner, and both of them burner has a bed connected to the DC motor, and we can make these rotations. And here, okay, this is a flow structure I want to mention. And in this experiment, we try to look at the flow voltage, the influence of flow voltage on the diffusion frame, which means that we need to generate a diffusion flame. In this case, for a loader burner, we try to mix the fuel and the nitrogen. We supply the fuel from the loader burner, and we impinge the oxygen from the upper burner. In the upper flow, the oxygen mixed with nitrogen. Okay, both of them, fuel and the oxygen, mixed with nitrogen to make it the balance. Okay, and this is the cold flow structures. When you do the experiment without burning, you can see from A, B, C, D, E, F, follow this sequence. We can see that the rotation speeds increase. You can see initially, okay, they will start to have some. You can see if you this one is omega equal to 0. That means the flow is e-rotation. We do not make it rotations. And for a given shot, we use the same shuttle speed. That means that the velocity actually is large enough to make the whole straight line complete, right? As the particle along the same line. You can have this is a long line, but when you increase the rotation speed, actually you will find out there is a small line, second segment. Now there's another long line. They tell you at this region, actually the flow velocity is too small. Velocity is small with the same shuttle speed. Shuttle speed is the same, right? But at this time interval, the particle has a small velocity, then the travel path becomes short. Okay, then you can see in this region, especially in the center region near the stagnation point, stagnation plant, they start to give you the loader very small flow velocity. That means that because you increase the injection velocity, most of the axial momentum convert to the radial momentum. Therefore, near the stagnation plane, the axial momentum is completely reduced, even reduced the minimum value, which means the flow velocity originally they will flow outward, radially outward. Down the value continue reduce to the 0. Then the velocity has the reverse directions point to the center. Okay, and in this case, you can see we start to have some recirculation occurs. But you can see actually this recirculation should be symmetric in both sides, as we plot it in the left hand in the left figures. But here you cannot see the circulation in the right hand side, right? Because this is due to the experimental problem. When you do the long-term observation, you can see a pair. Okay, but while I take picture, we do not see it, because at this instant there is no particle be carried into the recirculation. Okay, since those kinds of flow visualization depends on do we have a particle inside a flow. Without particles, you cannot see the motion of your particle of your flow. Increase the injection further, you can see there still show you there is the circulation is the in the left hand side. Also, you will see in the right hand side in the real experimental observation. Actually, they are both of them are exist. Finally, you can see in this case, actually the turbulent eddies occurs for the whole region, and this is a complete similar to the the figures shown in the left hand side. Okay, there is some eddy. You can see there is a vortex, small vortex. This is a cold flow structures. Okay, now if you try to ignite the diffusion flame here, okay, you can see this is very nicely a comparison between the cold flow and the hot flow. For the figure 8, the tell you originally this is the cold flow, and fuel coming from the lower burner, oxygen coming from the upper burner. You ignite it, then you have a perfect diffusion flame exist just at the stagnation surface, stagnation plane, right? And this is basically it's a purely diffusion flame, fuel supply from the lower burner and oxygen supply from the upper burner. Okay, now you try to increase your rotations. Actually, flame do not change too much. Okay, do not change too much. Be remember, as I mentioned, diffusion flame means the diffusion flame, the supply of fuel and oxygen depend on diffusion process. The influence coming on from the flow convection actually is a small influence. They just change their flame shape only, right? And in this situation, you can figure out in this because in this experiment we increase the flow rotation, right? Then near the stagnation plane, actually the flow velocity is reduced. That means the flow convection is reduced continuously. Okay, by this kinds of reduced convection influence, that means the support of the diffusion process for the diffusion flame remain the major play the major role. Therefore, the diffusion flame still exists just at the sit at the stagnation plane unless they produce a large region of a turbulent flow, then the flame become thick. The flame thickness is broadened, okay, to allow those kinds of AD move into your diffusion flame. Okay, this is a very nice experiment. But for this kinds of experiment, actually, we try to control the fuel concentration and the oxygen concentration. Then you do not have a soot can be absorbed from this set of experiments. But for the next part, we try to think about the nucleation of a subparticle here. The left-hand side tell you the experiment results. The horizontal line represent the flow locations, the rotation speeds, the RP the rotation per second. Okay, rotation speed omega we start increase from 0 to 8 RPS. Okay, and here they tell you we try to change the fuel concentration based on the if you fix the the oxygen concentration in the upper side 58.9, and then we change the lower fuel concentration to see when we can have a shoot. Okay, and the lower portion of this plot tell you we fix the fuel rate fuel concentration in the lower as 18.8%, but try to change the oxygen concentration in the upper part. Actually, these two experiments to let you know both of the fuel supply and the oxygen supplies will have some key factor to influence the soot formation. Okay, now let's look at the upper parts. Okay, here they tell you if you when you choose the oxygen concentration in the lower flow as the 58.5, you try to calculate at the point actually if you want to have a stoichiometric ratio between these two, the oxygen supply you need to supply the 9% fuel, and these two value 9% fuel with the 58.5% oxygen will give you the stoichiometric balance, stoichiometric supply balance, right? But you remember, even for diffusion flame, for any kinds of stoichiometric, any kinds of fuel supply oxygen, actually the diffusion flame will try to change their position to balance the supply, always stoichiometric. But in this case, we just try to mention for the initial conditions. from the upper flow and the lower flow, they are in the stoichiometric condition as the field equal to 9. Okay, but here they tell you from the experiment, if you keep the field concentration is 9, this 9 is the stoichiometric 9, right? Actually, without rotations, even in this, if you increase the 6th and 7th, actually there is no shoot occurs. Okay, which means that you need to increase the field higher than the original stoichiometric value of 9%, then you may have a shoot occurs when you have a smaller recirculation. Okay, then there is they tell you there is the boundary. The upper region you may have a shoot, the lower region you do not have a shoot. This is the inference basically coming from the fuel concentration. If you do not supply enough butane, okay, this is I think we burn the butane. A butane diffusion frame, okay, and then they will not, we do not have a shoot as the fuel concentration is not too much, okay. But for the lower portion, actually, we try to control. Now, in this case, we fix the fuel concentration as an 18.8% in the upper flow, and the corresponding oxygens basically is we do not calculate the stoichiometry. Actually it's easier to reach to a certain lower value. But here there is the air. Okay, if you there is a 21%, there is a limit here. And in this experiment, tell you when your oxygen lower than 21%, you almost do not have any shoot occurs even you increase omega. Okay, there is the no shoot region, and the upper part is a shoot layer. And if you increase your oxygen concentration higher than 21%, always, usually, if you have a suitable rotating speed, you still can have a shoot layer occurs. And the same features for the upper and the lower part tell you when you increase the omega. For the both case, actually, they will try to enhance your shoot formation. Okay, this is a tell you when you increase the omega, that means you will reduce the radial velocity on the on the stagnation plane, right? And since the diffusion plane exists just at the stagnation plane, this which means the radial velocity is reduced by increasing the omega. This increase, this reduce the radial velocity will cannot bring those kinds of carbon particle move out. Originally, near the stagnation plane, this radial velocity will carry your gaseous particle from the center to the outer surrounding, right? Then if you have some carbon atoms released by the thermal decomposition, those carbon will be bring out, will be carried out to the outer region. But in this case, when you increase the flow rotations, the radial velocity is reduced. Then you cannot carry too much oxygen or too much carbon particles out. Those carbon particles will stay in these regions, and they have a strong possibility to collect or interact each other to produce as a larger carbon particle. This is a reason why originally you will have a blue flame, but you increase the omega, you can see gradually the yellow color becomes very strong because there is the reduce the residence time by reduce the radial velocity increase by influenced by the increasing injection velocity. Okay, then should occur should layer occurs. Then from this experiment tell you some understanding for the criterion for should layer. Here they tell you the supply of fuel should higher than stoichiometric. Okay, you need to have a more fuel exist, then you can provide a more carbon source, and the oxygen should be richer than the original air compositions, 21%. And if you try to increase omega, it is very help will help the formation of shoot layer because you will when you increase omega, you will increase the residence times of the flow of the carbon particle exists in the stagnation plane. They will accumulate and collaborate, conglomerate together, conglomeration, and to produce a large particle subparticles.